Lesson 1. Data Representation and Number Systems. Welcome to the first lesson on MATSEC AM Computing Fundamentals. We begin with how computers represent data. To find the decimal value of a binary number like 10110101, you sum the place values of bits that are 1, from the most significant bit down to the least significant bit, which gives you 181. For a compact shorthand, we use hexadecimal, where each hex digit maps to 4 bits. For instance, the hex value 3F translates to binary 00111111, because 3 is 0011 and F is 1111. When dealing with negative numbers, systems often use 2's complement. In an 8-bit 2's complement system, the range is -128 to +127, where the most significant bit is the sign bit. To represent -6, you start with +6, which is 0000110. Invert the bits to 11111001 and add 1 to get 11111101. Another method is 8421 binary coded decimal, or BCD, which encodes each decimal digit as a 4-bit nibble using 8421 weights. The number 47 becomes 01000111. For fractions, fixed point keeps the binary point in a fixed position, while floating point uses a mantissa and an exponent, trading precision for a wider range. Normalizing a positive floating point number shifts the mantissa so it starts with a leading 1 after the point, maximizing precision, while the exponent is adjusted accordingly. Finally, for text, Unicode is preferred over the older ASCII because Unicode assigns code points for a far larger set of characters across many writing systems globally. Lesson 2. Digital Logic and Boolean Algebra. This lesson covers digital logic and circuit design. We start with the basic logic gates. A 2-input XOR gate outputs a 1 only when its inputs differ. If both inputs are 1, the output is 0. Interestingly, you can build any Boolean function using only NAND gates or only NOR gates, which is why they are called universal gates. In Boolean algebra, simplification is key. For example, using the absorption law, the expression A plus A and B simplifies simply to A. You also need to know De Morgan's theorem, which states that the complement of a product is the sum of the complements, meaning not A and B equals not A or not B, and vice versa. To simplify complex expressions visually, we use Karnaugh maps. In a 4-variable Karnaugh map, you can group 1s or 0s into rectangular powers of 2. You can also include don't care cells in these groupings if they help form a larger power of 2 group, though they do not have to be covered if they don't help. Logic gates are used to build arithmetic circuits. A half adder adds 2 bits without a carry-in. Its sum is produced by an XOR gate, and its carry is produced by an AND gate. A full adder differs because it accepts a carry-in as a third input, alongside A and B, allowing multiple full adders to be cascaded into multi-bit binary adders. Lesson 3. Computer Architecture and Assembly. Our third lesson explores computer architecture and assembly instructions. Under the von Neumann model, programs and data share the same main memory address space and are accessed via a common system bus. The address bus specifies the memory or I/O location being accessed. Its width limits the addressable space. For example, a 16-bit address bus can generate 65,536 distinct addresses. To execute programs, the control unit orchestrates the fetch, decode, and execute cycle by generating control signals for registers, the ALU, and buses. During the fetch stage, an instruction is loaded from memory into the current instruction register, or CIR, which holds it while it is decoded. To speed this up, Level 1 cache sits close to the CPU, providing very fast access to recently used instructions and data. In assembly language, an instruction includes an opcode, which specifies the operation to perform. We also use different addressing modes. Immediate addressing places a constant operand directly in the instruction, like loading a hex value into a register. Indirect addressing uses square brackets around a register to indicate that the register holds a memory address, and the contents at that address should be loaded. Finally, indexed addressing combines a base register and an index register, adding their values to form an effective address, which is highly useful for array-like access patterns. Lesson 4. Operating systems concepts. In our final lesson, we look at operating systems. Different tasks require different OS designs. For example, a real-time OS is designed to guarantee responses within strict time constraints. The OS manages multiple processes. A process enters the wait or blocked state when it is waiting for an event like I/O completion before it can continue. To share the CPU fairly among ready processes, round-robin scheduling gives each process a fixed time quantum in a cyclical order. However, processes can get stuck in a deadlock, which occurs when each process holds resources while waiting for resources held by others in a circular wait, resulting in no progress. Memory management is another critical OS task. Programs use logical addresses generated by the CPU, which the OS and hardware translate into physical addresses, referring to actual RAM locations. A common issue is memory fragmentation, where free memory is split into pieces too small to efficiently satisfy allocation requests. To manage memory effectively, paging is used. In a paging system, physical memory is divided into fixed-size blocks called page frames, each capable of holding one page of logical memory. Finally, when handling peripherals, interrupt-driven I/O is highly efficient. Unlike polling, where the CPU continuously checks device status, an interrupt allows the device to signal the CPU only when it is ready, freeing the CPU to do other work in the meantime.
Thanks for watching. For free practice questions, study guides, and flashcards, visit exampreprise.com. Good luck on your exam!